All right, so now that we've talked about our IMFs, what we want to start to do is understand how our intermolecular forces can result in essentially different types of solids and different properties, okay? So our types of solids, first of all, right, let's talk about our ionic solids. Ionic solids, of course, have positive and negative interactions. We've got really strong ionic interactions, so our coulombic forces are going to be really strong. The intermolecular forces within these are going to be really strong. Okay, so that results in, of course, being a solid at room temperature. At room temp, right? But it also means that it has a very high boiling point and a high melting point, because for us to melt those ionic solids, we have to start breaking some of those intermolecular forces, okay? Then let's talk about our covalent network solids. So a covalent network solid, right, what it has is this kind of repeating units of covalent bonds, right? So we're going to have these repeating units all the way throughout, okay? Covalent network solids, these solids have this repeating unit of covalent bonds. So really, there's not really an intermolecular force within this. We have molecular forces where we have these repeating covalent bonds. So this results in them being a solid at room temperature. But if we were to try and melt them, right, we would have to break covalent bonds. So that means that it's going to have high melting point and boiling point. Okay, so it's obviously really hard because we would have to break a covalent bond for us to melt or for us to boil the compound. Okay, generally, because they have all of these covalent bonds, they're not going to want to dissolve, right? So low solubility. And then the other properties kind of depend on the type of covalent bonds and the types of interactions that we have. All right, so generally we think about having low conductivity. Low conductivity because, right, all of the electrons are tied up in these bonds. So generally, we're not going to be able to move electrons around in here. But some examples that we would have of this, right, would be diamond or graphite. So if we think about diamond versus graphite, both of them are just carbon bonds, but diamond has these kind of, all of our pieces, all of our carbon bonds are attached all the way throughout. Whereas graphite essentially has kind of layers, right? So it's got these layers of bonds, and when it has these layers of bonds, we're able to kind of shear off one layer at a time. So our covalent network solids, really the properties of them depend on the type of bonds that we have in there. Okay? Our next piece, our molecular solids. Molecular solids are kind of similar to graphite, except we don't have as large of a array of bonding. Okay? Really, it's just an array of molecules and this array of molecules are held together by the IMFs. Okay? So that means if they're going to be a solid at room temperature, overall their IMFs, when we add them together, are really going to be pretty strong, right? If they're going to be a solid at room temperature, the IMFs have to be really strong to hold those particles together, okay? So oftentimes, molecular solids are going to have be really large molecules, okay? And if they're really large molecules, that means that they're going to have large LDFs, okay? And there's going to be this strong covalent bonds within them, and then weak London dispersion forces, okay? With the really large molecules, that means that it has a really large electron cloud. With a really large electron cloud, we're able to kind of push that electron cloud around fairly easily. That pushing around of the electron cloud is London dispersion forces, okay? That's the result of us randomly being able to move the electrons around, okay? So the larger the electron cloud, right, the easier it is, the stronger the LDFs, okay? Now, metals. Metals, we've talked about a little bit, right? We've got this array of positives. That would be the nucleus of the metals. And then we've got negatives, right, that are kind of not really associated with any of those positives, because those positives, right, our metals are not very electronegative. So they're not really going to be holding on to the electrons very strongly, okay? So we've got negative charges that are able to kind of move freely. So that results, of course, then in high conductivity. That results, this arrangement of positives, right, results in high malleability, right? We're able to, malleability, there we go. High malleability because we can kind of move some of these atoms, right? We can move some of the positive charges, and that movement doesn't really change what the other positives are seeing. So we're not really changing what they're seeing, so that's not going to really change the structure. And so then we can kind of do this bending of the metal to and not really change the metal, so it's still going to be bound together, okay? So the large biomolecules and polymers, really this is oftentimes some of our molecular solids and kind of our covalent network solids, okay? These are going to have lots of different types of IMFs. So let's see, multiple types of IMFs. That type of IMF can obviously then affect the properties. So a large biomolecule, if we think about a fatty acid chain, right, we've got long fatty acids, right, and then it's kind of bound up here by something. We're going to have long fatty acids. All of these carbons that are in here, carbon and hydrogen, right, that's going to be a nonpolar bit over on this side. But we've got lots of nonpolar interactions. The LDF, the London dispersion forces, we've got lots and lots of London dispersion forces. So that means that it's going to be relatively solid at room temperature, right? Think about butter. Butter is just a whole lot of fats. That's what this is right there, okay? Other examples would be like a polymer, where we have repeating chains of maybe a carbon ring along with a chlorine kind of coming off, right? And we're going to get these large, maybe dendritic type of polymers, right? Maybe it's like that, or we've got kind of this long chain of polymers. Depending on what we have, right, that's going to affect our properties, okay? So if we've got a really long chain like this, right? Maybe we just have lots of London dispersion forces. This would be something like our PFET or PTFE. PTEF or PTFE. I can spell. I'm sorry. PTFE, right? This is a polymer, a plastic. This plastic, the properties of the plastic are controlled by the type of polymer and the type of intermolecular forces. Okay? So, hopefully, we can start to associate some of our intermolecular forces with some of our properties of our solids.